Hey guys, and welcome back to another video on the channel. Today we're going to be introducing Green's theorem. Green's theorem is a particular theorem you can use to evaluate a line integral such that it has a closed region. Okay, so if you consider you start here and you traverse some path to here, and then you go back this way and meet up at that same point. And let's say you're going along this direction here the entire time. You can apply Green's theorem pretty much because this here is a closed region along a particular path C. So the path C is pretty much the line integral. So the path C would be this entire path going all the way around, all the way around here. That's terrible highlighting skills, but you know what I mean. So if you had a vector field, so imagine I'll just draw some random vector field where a vector is in every point in every space, and you went through that field, you could work out the work done on it, pretty much, okay? If it went in a closed region though, okay? So in other words, the way we set up Green's theorem is, alright, we want to work out the integral of a particular path C through a vector field along some pretty much path, okay? So that is pretty much equivalent to just integrating the separate parts of the vector field. So for example, a vector field is given up pretty much as a function in the x direction, so let's call that p, and a function in the y direction, which is called j. Okay. So in other words, you can rewrite this expression up here as pretty much p dx plus q dy. Okay, because this r will represent x and y anyway, pretty much. So Green's theorem pretty much states if you have this scenario here and C is a closed counterclockwise region, so I'll just call closed region, because if it's counterclockwise all you gotta do is chuck a negative sign in front of it and then you can apply the theorem. But if it's a closed region, then your particular path, and you can use a circle in our integral now because it's a closed region, a contour integral. So if you integrate along a particular path C with a vector field like this, this is going to be equivalent to the double integral along some other path D, where D represents between x and y, of the partial derivative of q with respect to x minus the partial derivative of p with respect to y, and then dA, where dA represents pretty much dx dy. Okay, it's just a shorthand for it. So this here is Green's theorem. Let's see if I can write that fully. I think I spelled theorem right. Hopefully I did. Okay. So the best way to see this pretty much is in an example. So consider this following scenario. You've got this vector field in space. So you have f of x and y, and you have this field. So you have x, y, I hat plus x squared j hat. Okay. So you can imagine this vector field. So at every point in space, there's a particular vector, and it corresponds with pretty much this function here. So if you want to work at the vector at, let's say, the point x equals 1 and y equals 1, you would substitute in f of 1, 1. So you should get 1 here, and you should also get 1 there. So you get j. So you have this vector here with a length of √2. Now you'll notice as x gets very large, this term is going to get pretty bigger than this term here because of the squared factor. So you imagine the y component is going to increase for each vector. So you'll have some vector field looking like this over time, just from looking at it, pretty much, not just from graphing it, just from looking at it. Okay, so what we want to work out is imagine that vector field permeabiliting pretty much this 2D space, and we want to work out the work done on a function that goes through pretty much a unit circle, so a unit square, sorry, that goes from this point here to here, to here, to here. So it goes like this. Oh, that's terrible. So it starts at 0, 0, goes to 1, 0, then goes to 1, 1, then goes to 0, 1, and then back to the starting point. So this is our closed region here. Okay, so this line integral, this is our path C. Our path C is going around here like this, pretty much. Okay, So it's not as arbitrary as the drawing I had up here, where this represent my path C. This here is now my path C, the purple region, sorry. So the way we can start writing it is to work out our work done is pretty much the integral. Now we can go closed region of C of F dotted with R. Now we can recognize what this looks like. This here is my P, and this here is my Q. As you can see there, that's my P, and that's my Q. So that's going to be very important when we write it out. So we can write it out like this. The integral of our closed region C of x, y, I plus x squared j. Okay. Now, Green's theorem, just write the double integral. Now leave the bounds for now, and you want the partial derivative of this function here with respect to x. So x squared minus the partial derivative of that with respect to y. Now, if the vector field is conservative, this whole thing would be 0. So what I mean by conservative is a vector field is conservative such that the partial derivative of this guy here with respect to y is equivalent to this derivative here. Now if you take a look at it in the actual theorem itself, this bit here is exactly the same as this. So if it was conservative, this thing would be 0 pretty much. So that means the work done on a particle through this vector field would be independent of the path pretty much. But in this case here, I don't think that will be the case. Okay, and then I'm just going to put dA here as well. Okay, so if we take a look here, we got to work out our bounds pretty much because dA just represents dx dy. So it's like a double integral. So we'll rewrite it like this, and we'll leave the bounds empty for now. Partial derivative of x squared with respect to x is going to be 2x. Partial derivative of all this with respect to y is going to be x because x is treated as a constant, so our variable y just turns to 1, so you have minus x here. So the whole thing pretty much is just going to be double integral of pretty much just x dx and dA, sorry. Okay. Alright, now I can replace the dA with pretty much a dx dy. So I have the double integral of x dx dy. Now let's take a look at our bounds. So what we need to do is look where x and y change. So x goes from 0 to 1. So 0 to 1 is my x bounds, and y also goes from 0 to 1. So we'll go 0 and 1. So that means our double integral is pretty much 0 to 1, 0 to 1 of x dx dy. Now the way you do a double integral is you treat the other variable as a constant when you integrate. But to start off with, we all got to do is integrate with respect to x. So when you integrate x, it turns into x squared over 2. So you'll have x squared on 2, and then you've got your bounds. So 0 and 1. Plugging in the 1, we get a half. So the integral of 0 to 1 of a half is what we have left, pretty much. Integrate with respect to y, so we'll have a half of y, 0 to 1, and you'll get a half. So the work done when this vector field is permeabilitying this space here, when the particle goes in this square motion, the work done will be a half joules, pretty much, okay? That was an introductory question of Green's theorem. I'll be doing another one very shortly. If you want to check that out, that video will be up very shortly. But if you did enjoy this video and you have any questions, leave some in the comments below, okay?